Any form of power generation that utilizes fluids in any way, shape, or form probably has the use of turbines somewhere along in the process. Right? We have bladed turbines that are used in hydroelectric dams, for example, which are rotated using the high pressure water to create electricity. Today, we're going to look at one such turbine created by Nikola Tesla, aptly named the Tesla turbine, which was invented back in 1910 to 1913. We're going to talk about some of the advantages it brought and a lot of disadvantages. So, to understand how effective this really was, let's first take a comparison between traditional bladed turbines that are mainstream today and Tesla turbines. So, as you can see in the image over here, bladed turbines use the concept of a lift force to turn the blades. Say you have a flat stone and you throw it in a river. Now, when water is moving all around it, you sort of notice sometimes that the stone moves, and that is because of the lift force. These bladed turbines are built aerodynamically to maximize that particular force, creating high speed rotations. Bladed turbines, on the other hand, use the concept of torque and what is known as the boundary layer effect to turn these disks. Another name for these turbines is actually the boundary layer turbine. So it's a fitting name. This image over here shows a very simple implementation of Tesla's turbine. Now you have a disk on an axis, and say you have a water hose where the stream of water is parallel to the tangent of the disk. This uses the concept of a viscous force to rotate these disks. The question now is, what exactly is viscous force? What exactly is boundary layer effect, right? So let's look at this image over here first. This is a more industrialized version of the Tesla turbine where a casing was added to make things more efficient. Now you have an inlet where the pressure is significantly higher than atmosphere, and the outlet which is at the center of the disk with normal atmospheric pressure. And because of this, this obviously creates a suction effect where the fluid moves from the inlet to the outlet. Now, it is the boundary layer effect and the viscosity that really adheres the liquid to the disk and creates the rotation. So, let's look at what really the boundary layer effect is and how it works. Now, say you have a surface. Well, for the sake of reference, let's say this surface is one disk of the Tesla turbine. And there is a fluid flowing around it. The first layer of molecules in the fluid will always adhere itself to the surface. And then the second layer will flow on top of it slower, but will apply a force attempting to pull it along to have it flow along with the rest of the molecules. And by doing this, it loses energy in the process. Now, subsequent layers will all perform this exact same action, all of them losing energy, creating what's known as drag force. Now, as you can see in the image over here, this only happens for a certain amount above the surface. Everything outside of that is a free flow, where the flow is not relative to the layers. So, in the area where this effect happens, it is called the boundary layer. And the effect in itself is called viscosity. Obviously, more viscous liquids have stronger forces attracting between the molecules within the boundary layer. So let's look at steam, for example, which is what the example we are going to take for the sake of explaining this concept. Now, let's talk about how steam in particular for the boundary layer applies to the Tesla turbine. Now, what Tesla did was when he saw this effect, he added two parallel plates to that one existing plate, right? And they look something like this image here. They all have boundary layers, but they also have free flow. The thing is, free flow doesn't really contribute much into the system, if anything at all. So a way to make it more efficient would be to completely eliminate that. Tesla discovered that for steam, the boundary layer is roughly 0.4 millimeters. So what he did was that he made the distance between the blades two times the boundary layer. Therefore, on both surfaces have boundary layers only without the free flow. This means that any fluid that flows between these disks is affected by viscosity. Now, let's look at how this creates motion for the water. So now we know, for one, that there is a difference of pressure between the inlet and the outlet, so the water is naturally going to try and move to the center. But there's also a very strong force from the inlet because of the high pressure. So we have one force going downwards, and we have another force going tangential to the circle. So this creates a resultant force of somewhere in the middle, right? And this force is applied at every single point, which creates a spiral. This means that the higher the speed of the water at the inlet, the more spirals it's going to create. This is because the fluid is weaker at closer it is to the outlet because of the fact that it loses energy to the disk, potential energy to kinetic energy, and that creates the rotation. So there is a proportion value between the speed of the water and the number of spirals. The higher the speed of water, the higher the spirals. Therefore, the more rotation of disks. So that's how the water actually rotates the disk. So now we know how it works. Let's look at the early implementations that Tesla made for this particular device, right? Now, Tesla discovered that by increasing the area between the fluid and the turbine or the disk, there can be more torque produced, therefore more energy. So what he did was that he made it 8 blades, right? So as you can see in this image here, each of these disks were about 6 inches in diameter in this very small form factor. Tesla marketed his idea as a powerhouse the size of a hat. So it was really small in size, and it was theoretically very, very efficient. Now, when he created the design, he estimated that it would be able to create upwards of a 97% of efficiency, which is absurd considering at the time most bladed turbines had an efficiency of 40 to 50%. Now, his idea of doing this to create more torque backfired spectacularly because the sheer amount of force meant that these turbines, these blades, rotated at 35,000 rotations per minute. Now, while there is a centripetal force, rotation also creates another force called the centrifugal force. This force acts away from the center of the circle. The higher the speed, the higher the centrifugal force. And because the speed was so incredibly fast, the centrifugal force was so immense that the blades ended up warping, as you can see in the image over here. So Tesla decided that he would reduce his speed to less than 10,000 rotations per minute. So let's look at a couple of his ideas on how he chose to limit the RPM at the same time create high efficiency. So let's look at his first attempt, right? We have over here where he limited his design to 10,000 RPM and changed the diameter of the disc. So we can look at the specifications here, right? Still 8 discs, diameter went to 30.4 cm. This machine over here, which was only 5 kg in weight, was able to produce 100 horsepower output. Already very impressive. But Tesla chose to tune it further. While still keeping the speed at 10,000 RPM, what he did was then change the diameter of the disc even more to 24.8 centimeters. And this was able to create an even higher output of 110 horsepower. Very impressive, right? And his testing seems quite efficient. So Tesla then chose to demonstrate this to a number of engineers. He completely pushed the limits. Made a turbine which diameter was 45.7 cm with a 9,000 RPM limit. This small contraption was able to produce 200 horsepower output. This wasn't particularly big, as you can see in the image over here. The problem was, in his demonstration, rather than showing how the mechanics of his system worked, rather than showing the spinning of the discs, he instead chose to demonstrate the power of the machine. So, in all of the engineers who wanted to see the spinning disc didn't really understand the point of the demonstration. However, he was still able to get a number of investors. So things seem to be looking bright. Except a couple of problems. 3 things in particular. Why did it fail? Number 1 was that it was steam powered. Steam powered in a world where steam engines were falling out of favor and things like internal combustion engines were much more accessible to both engineers and regular citizens alike and were becoming much more popular. Second is the high RPM. Now, because of that increasingly high RPM, the theoretical value of 97% efficiency was not achievable because there was no material that could sustain the 36 or 35,000 RPM rotation. Therefore, no machine could be fully efficient. So if you wanted it to work in any capacity, you had to slow it down, and that reduces efficiency. So it was less popular there. And third, and perhaps the largest factor, was World War One, where internal combustion engines became very highly promoted comparatively to something that was still very much in the experimental stages. So that ended up failing spectacularly. So the question now is, are there any new applications of this particular concept? So let's look at a couple of things. We know the idea of viscosity can create movement in fluids, right? So let's focus on that in particular. Let's put aside power generation. This is what's known as a desalination device. Now, by attaching a torque motor to your Tesla turbine and creating rotation rather than through fluid through that motor, you can sort of create a pump because a liquid can flow from the inlet and can be compressed to a very high pressure and then out at the outlet. So the desalination device essentially acted as a vacuum pump. Now, by reducing the pressure in a container and then heating it to boiling point using the Tesla turbine, it would change it to steam, right? And then that steam would go through the turbine, condense into distilled water, and still move fast because of the high viscosity when it comes out the other side. So this could be a method. This device over here is shown for demonstration purposes only, but this concept could be applied to make desalination process much more easier and much more accessible, especially to people living near the sea. This uses the concept of viscosity to move liquids rather than using moving liquids to create rotation. Another application is the centrifugal pump, right? Now this provides extremely high flow rates of fluids, and it uses the same idea of rotation within a Tesla turbine to pass the velocity in the direction of a particular fluid. Right? It has hydraulic components that turn this disc, and the pump is mainly used to change the velocity. Right? This particular centrifugal pump or centrifugal devices are used in biomedicine and have been in research for upwards of 30 to 40 years and are still very applicable. Now, this entire idea of, you know what, let's attach a torque motor and create rotation rather than using fluid to create rotation is what later became known as the Tesla pump. So, that's all well and good that the concept of viscosity still has a place. The question is, why can't it work as a power generation method today, now? So, to do that, we need to look at the comparative between bladed turbines and Tesla turbines today. Let's look at modern bladed turbines. They already have a higher than 90% efficiency in most industrial applications. With a spec list that's something like this, right? Let's say for industrial purposes, we set a size of 3-meter diameter blades, right? These things rotate at roughly 2000 to 3000 RPM with a blade tip velocity. So the velocity at the tip of the blade, where it rotates, where it travels the most, is Mach 1.8. Now that is 1.8 times the speed of sound. Still very manageable and very applicable today. Tesla turbine, on the other hand, becomes more efficient as the speed increases. So if we even want to match industrial usage that already exists, we'll need the disc to be 3 meters as well, which in theory will need rotations of upwards of 50,000 rotations per minute, which already sounds very absurd. But to make it even more crazy, it would need a tip velocity of Mach 13. 13 times the speed of sound. Even today, there is really no material that can sustain such immense forces. Not carbon fiber, probably not even titanium or titanium alloys. So there is no incentive for people to advance this technology as a way of power generation, because traditional bladed turbines already have more than 90% efficiency in most cases. So what have we concluded from this speech? Tesla turbines, the concept of using viscosity to create movement, be it the movement of the blades or movement of fluids, is relevant because it's being used in the very niche field of pumps and centrifugal forces, amongst other things. But as a form of power generation, I do not see it becoming mainstream in even 40 to 50 years because of how efficient bladed turbines already are. But the concept of viscosity is very interesting in the sense the potential that it can bring in fluid mechanics and moving fluids is very high. And for that reason, I believe the concept still very much applies today. That's it. Thank you for your time.